Hello, students. We will start in 5 minutes, waiting for some more students to join. So, hello everyone. In previous week, the week 3, which was, so the topic was Fourier transform topics were there. And myself, Annu, I'm teaching you today's some of the contents related to Fourier transform, some tricks related to Fourier series, and the related questions. Okay, so I'm just waiting for some minutes for others to join. Actually, this course is being taught by the professor of IIT Mandi and IIC Bhopal. So basically, we have three TAs. So that's why I cannot see more attendees here. But even if you join, it's just a refreshment for you, all of you. So you can just join and be here in the class. And okay, so these are the outlines which will go through. Fourier domain representation, definition of the Fourier series, Fourier transform examples, Dirichlet conditions, and the inverse Fourier transform, Fourier time uncertainty relation, Fourier analysis review, ideal filter types, practical analog filters, and putting all it together some filters. We will also see some of the practical examples using Python code. Okay. Okay, I'm starting the class now. So first and the foremost question arises in our mind is, why do we need frequency domain representation? Or why do we need frequency domain uh, analysis? So answer is, in practice, in real signals and system, we convert the time domain signal to frequency domain to analyze the spectrum. Okay, the first question answer is to analyze spectrum or bandwidth. Okay. So, if you know, you often have come across with the licensed and unlicensed band in 5G, 6G, and 4G. So, people all, 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 the range of frequency is there, and that spectrum is very for application. So application ranges from broadcasting a television channel or FM radio, AM radio, and different applications. So different application, but any application that involves connectivity uses this spectrum. So even if you communicate, that communication is happening in a particular frequency. That is an audio frequency. Okay, or speaking frequency. So I'm speaking. So that is a frequency. Speaking frequency is how much? 0 hertz to 3.6 kilohertz. Okay. And if I say up to what frequency range I can hear is 20 hertz to 20,000 kilohertz. Okay. So that is the frequency range. So this is scared and we need to utilize it efficiently. So the researchers around the globe are doing resource allocation and optimization so that the resource here means the time and bandwidth so that it is optimized properly. So whenever all the physical occurring signals, we convert it to time frequency domain from the time domain because in practice all are analog in nature and physically occurring signals are analog in nature and they are time varying. Okay, so a signal that as I told in the first class, a signal is a physical quantity that varies with respect to independent quantity. So independent quantity here we talk about is time. In other case, it can be a temperature or pressure, but we often come across with the time. Okay, so details is about transforming a time domain signal to frequency domain from form reveals its frequency components. Okay. What frequency components it consists of. So if we say the Fourier transform of a signal x is defined as x of f equals to transform. Fourier. So Fourier is just a name of scientist. Okay. And if you want to convert it to frequency domain. So for example, a sine wave that we often model associate and if you want to convert like what frequency it consists impulse frequencies at plus f plus minus f naught. So this gives this idea. Okay, a sine wave produces impulses at frequency. This is the property, and it also provides a way to analyze signals by decomposing them into sinusoidal components. Fourier transform also provides the way to convert into my tablet is lagging. I don't know why it's not showing here. Just a second. So the inverse transform recovers its original signal. Just a second. So sorry for the interruption. So yes, I was talking about the Fourier transform provides a way to analyze signals by decomposing them into sinusoidal components. Now, the inverse Fourier transform, okay, it recovers the original signal. So in inverse Fourier transform, you have xf e power j to pi f t df. Okay, and for example, a Gaussian pulse is transform is also a Gaussian. A very interesting thing to notice. So we have a Gaussian signal. Okay, the Gaussian signal will looks like this. It gives a transform in e power minus pi square f square a. So what I basically interpreted here is t square. So this is giving an Fourier transform. So that's why a Gaussian wave doesn't change its nature even after a Fourier transform. That's why we model the noise in communication system by a Gaussian pulse. So a Gaussian pulse never changes its shape even after a Fourier transform. That's interesting to note. Okay. So if I talk about the applications, so frequency domain analysis is very crucial in the fields like communication systems, audio processing, and medical imaging. So in mathematics, it utilizes properties such as linearity and symmetry. Examples are audio signal processing to isolate different frequency bands. So MRI imaging reconstructs partial information from the frequency data. So MRI imaging reconstructs spatial information from the frequency data. So if I talk about the MRIs in the medical term, and imaging reconstructs a spatial information, whatever the information are there from the frequency data. So that's why we are converting the time domain signal to a frequency domain signal. Okay. So these are the properties. So Fourier transform converts a time domain signal into frequency domain representation as we know. So note that this x is small x here, but for after Fourier transform, it's not the same function. That's why it is capital X. It's not same function. So people often get confused just the x inside this f. No, this x in small x and capital X is different because these are the two different functions. And if I talk about xt is equals to e power minus at ut, what will be the x of f? So it is 1 plus a plus j omega. Okay. E power minus at ut, Fourier transform is a plus j omega. Okay. Now we will solve this question later. So there are some properties of Fourier transform. So key properties include linearity, time shift, frequency shift, and the scaling. So if we do, now I want to say about the full transform is in omega domain. So people often get confused with omega, like if whenever where to come with this 2 pi. Okay, forget about it. So we should know the basic formula. So suppose we have xt and this is giving xf. So xf is equals to minus infinity to infinity xt power minus j 2 pi ft dt. Now, if I talk about what will be the x of omega, so omega is nothing but 2 pi f. So, this is nothing but minus infinity to infinity xt e power minus j omega t dt. Okay, this is 2 pi f omega t dt. Now, if I talk about what is the inverse Fourier transform, so x of t is from x of f. Let's t from x of f. So what is this minus infinity to infinity x of capital X of f e power j omega j 2 pi ft df. Okay, this is df. Now omega is 2 pi f. So how will you represent in terms of omega? So this will be replaced by x of omega. Now this will be replaced by x of omega. So this is j omega and c. df will be replaced by d omega how much? So it will be replaced by 1 by 2 by d omega. Why? Because omega is equals to 2 pi f. So here df was there. So that's why 1 by 2 pi came. You should not confuse with that. So here this is understood. I hope you understood. You should not get confused. You should only remember one type of frequency transform. Okay, Fourier transform. And then you should be able to change it. People often uh, this keep this in mind and confuse it. Okay, they should not do rattabazi. Okay, so we will go to the properties of, and you should be able to do this properties analysis with respect to omega and frequency domain also. You should remember one thing, you should be able to convert it to other one. Okay, so if I talk about linearity, linearity is nothing but if we take Fourier transform of axt plus byt is equals to axf plus byf. So it is simply the superposition and scaling. Okay, so time shift if I say, so whenever we do the time shift in time domain, so it is a xt minus t naught, then in frequency domain will be multiplied by e power minus j2 pi f t naught. Understood? This is multiplied by e power minus j 2 pi f t naught into xf. And wherever, what if you want to do the frequency shift in the frequency domain? So in that case, it will be multiplied by e power j 2 pi f naught t. Then it is the Fourier transform next x of f minus f naught. So it is plus here, so it is minus here. Whereas in time domain, if it is x t minus t naught, then frequency transform is, I never forget this because this is trick, okay? Minus f t naught x of it. Okay, so this is very important. Also, a time shifted delta function transforms to e power minus j 2 pi f t naught. So do you know what is a Fourier transform delta function? It's just one. Okay, so you are shifting in a time domain, so it is shifted by e power minus j 2 pi f t naught. Okay, now let us solve some of the basics calculations of Fourier transform. So one of the basic Fourier transform of calculation is for the rectangular pulse. So rectangular pulse can be represented as xt. What do you mean by mod of t less than or equals to t by 2? So this means that t is minus t by 2, t by 2. Okay, so this is nothing but 1 here, t by 2 minus t by 2, otherwise 0. Now, I want to show you why this is coming out to be this. So the answer is nothing but if you solve in a proper formula, it is T sync FT. Okay. So it is T sync FT. And I'll give you one trick that you never forget in ever in life about this trick T. Okay. So suppose we have this is A and this is XT. This is T. T by 2. So two properties I told, that is scaling, shifting, and linearity. So that was very simple. Here I will tell you the duality. Duality in Fourier transfer is of prime importance. Okay. So you have Fourier transform here. So what will you get here? So I am dealing usually in frequency term, not in omega. That is another reason because I know always to convert the frequency to omega. So that never bothers me a lot. So F. This is X. So what will be the Fourier transform of this? So answer is A tau sync F tau. Tau here is T. Okay. So what does mean this and what is this? So sorry. This is area. This is pulse width. So any rectangular pulse, whatever the area will be there, that will be the amplitude or the scaling factor, and inside that is the pulse width. So pulse width is T, right? And the area of the rectangle is A into T, isn't it? So that's what it was. Okay. So this is what now what duality states that. So I'm talking about the duality. It's very, very important. So in practice, in the time domain, I'm just writing it again. This is time domain. This is frequency domain. Okay. So I will do this, and do this. Remember, this is the left side is time domain, the right side is frequency domain. Okay. Moving back to another color. Hmm. So this is duality, what it says that. And if you do this with the same sign, this is capital, but in the time domain, it is capital again. But if you do in time, okay, and if you this is T. So here this is 1 by T, this is 2 by T, this is minus 1 by T. What is this? This is A. Hmm? So again, this is 1 by T, this is 2 by T, this minus 1 by T, minus 2 by T. So it is actually the even multiplication of the natural number multiplication of one frequency. So 1 by T is a time period. This is A. And duality says that this will go here, x of minus F, and so what is x of minus F? Since it is even signal, so x of minus F or x of F is same. But remember this, the function is same. Okay. Small f is there. Okay. And this is A, this is minus T by 2, this is T by 2. Very interesting. Okay. So what I'm trying to say is whenever we have this duality, so that is giving x of F, then x of T, this will give to x of minus. This is a frequency, sorry, this is time domain. This is the frequency. The property is called duality. Interesting to note, right? Okay. So this is area, this pulse, you should never forget this. So this is what. But in practice, you might wonder. I have one question. So whenever we want to transmit the signals then we convert it to bits and bytes, right? And then we transmit it to higher frequency, because right now the frequency of 5G is what? It's ranging from gigahertz, some sort of gigahertz. So suppose simple ITS frequency is 5.9 gigahertz, or the licensed band or N78 band is 3.7 gigahertz. Okay. So in gigahertz frequency, do you think that we can transmit this but small signals? No. So what we do is we convert it to a digital. Okay. Then we represent the signals in ones and zero. And then the ones and zeros are transmitted in terms of pulses. So now the question is that the same pulse is a rectangular? Is this the same pulse like this? No. Answer is no. We don't do that. Why? Because if you see, the pulse width is having that bandwidth of finite bandwidth. Okay, sorry, in this is time domain. And if we convert it to frequency domain, the bandwidth is infinity, isn't it? Ideal bandwidth is infinity. This is another color I'll take. Ideal bandwidth is infinity. But whenever we transmit it to sync funds, okay, then the proper bandwidth is T here. That is not infinity, that is fixed. Some sort of bandwidth. So in practice, we transmit raised cosine pulse. This is called pulse, not raised cosine pulse. So what we do is we have this raised cosine pulse in the time domain. Then we apply filter. Then we get this. Okay. Then we get this. And we finally transmit it to antennas. Okay. Because this is having the ideal bandwidth of is finite. We are concerned about this. Okay. So this was all about that. This example is fundamental in digital communication for the pulse shaping. Very, very important for the pulse shaping. Now, Fourier transform examples are sine wave. So we have to analyze the transform of a sine function. So for example, suppose we have sine this. So my question is, using Euler's formula, what you can write is sine omega t is equals to e power j omega t minus e power minus j omega t divided by 2j. And as we know, e power minus at was nothing but 1 upon a plus j omega in the frequency domain. So since this is nothing but at is not there, this is omega, this frequency domain, and we know that if we want to shift in the time domain, suppose this was x minus t naught, this is shifting to e power minus j uh, 2 pi f t naught x of f. And if in a similar way, if we do here x t e power j 2 pi f naught t, then it is going to x of f minus f naught. Isn't it? That the formula that we were seeing it. Since there's no function here, but just a function, so it is 1, 1. So the 1 Fourier transform is 1 upon 2j. Let's keep it out. So this is del. Okay. And so this is giving plus to minus here. So this is nothing but f minus f naught, because this was f naught, omega naught was there. You can see f naught is there. Okay, so minus del f plus f naught. Very interesting note to note. So you can see the transform shows impulses at frequencies of plus minus f naught. So sine, which looks like this in the time domain, is giving the Fourier transform at Is it small x? No, it is capital X. And it is giving the frequency transform. And what is the and magnitude of this? It is minus. Right? This is minus. And if you say the positive magnitude, the j will go because mod of j is no. Okay. So the sine frequency carries a single frequency or the single tone. So that's why sine frequency is a single tone. Okay. And we also saw very great news is the Gaussian function retained its shape in even the frequency domain. So for the transform of Gaussian function, the frequency transform is also Gaussian. That is very, very important concept used in optics and the probability theory. What if it is multiplied by a here? So here it will be multiplied by a, divided by a square, sorry. So what we do is, so sorry. So I'm telling you the formula. If x of 80 is there, then it is given by x of f by a. Simple formula you can apply. This is capital, this is small. Okay, well and good. So we know the transform rectangular pulse will demonstrate its sync behavior. For the pulse of t, it shows us the trade-off. This example shows a trade-off between time localization and the frequency spread. I'm giving some of the practical real-time examples. Okay. Now, there's very important concept in frequency transform, the Fourier transform, the Fourier series, that is called Dirichlet conditions. Okay, so Dirichlet conditions are the criteria for a function to have convergent Fourier series. Now, you may wonder what is Fourier series? Is this same or the linked with the Fourier transform? The answer is no. The only link between these two is the sign test. Okay, so Fourier series is just a way of representation of periodic signal in the sum of sine and cosine in time domain. Whereas Fourier transform is talk about frequency domain. This doesn't talk about time domain. So what I would like to repeat, Fourier series is a way of representation of time domain signal that is periodic in nature in the sum of sine and cosine. Now you will ask why we want to rewrite. Because periodic signals are infinitely durated. Now you want to write in terms of harmonics because it will repeat after that. And as you know, sine and cosine signals are carry single tone frequencies, isn't it? Right? So you want to write in terms of harmonics of sine and cosine. That is fundamental frequency. So that I will tell you how it is done. Okay. Now, requirements includes the finite numbers of discontinuities and extrema in a finite interval. So if a signal is given to you and it should have the finite number of discontinuities, it should have finite number of extrema, the maxima and minima in a finite interval. For example, a square wave, which is a piecewise continuous, meet this criteria. Okay, so these criteria must be fulfilled. Now, it should be absolutely summable also. If we do integration over minus particular time interval, it should be less than, very, very less than infinity. So finite number of discontinuities, continuities, absolutely summable, and finite numbers of maximum and minimum. For example, sawtooth functions, triangular waves satisfy these conditions. There are some examples. So if I take the tan function, suppose, so how it looks like, this looks like this. Isn't it? So do you think it is having the maximum, minimum finite? No, it is going up to infinity. It's not also absolute summable. But if it is defined on a restricted interval, suppose this is, then you can do. If it is not defined, then it is not. Okay. So this is one of the example. Now we'll talk about Fourier transform. Let's see some of the inverse Fourier transform examples also. It is used in signal reconstruction in communication systems. Okay, And the formula is simple, but like this. Okay, so you see this formulas. Meanwhile, I'm coming from in just 2 minutes to have water. So I hope you understood this particular inverse Fourier transform. So derivation uses the orthogonality of two complex exponentials. Okay. So this is the formula inverse Fourier transform. So utilizing this particular thing, we arrive at the inversion formula. So even if you want to derive it, you can derive Well and good. Okay, so that is very fundamental in solving the differential equations via Fourier transform. Okay, so moving to some of the inverse Fourier transform relationships. So this I already told you using duality. Duality is one of the best thing that can be used in this sinc and the pulse functions. And you should know the practical application and implications of that. So it is very, very important in filter design and signal reconstruction, this particular sync function. Okay. So, uh, so if I say, uh, this is what, let me draw this. So have you wondered that this Fourier transform, when we talk about that is written in a capital letter, but if you say in the time domain, then it is in the small letter. So that is also one of the thing that you have to note and keep in the mind. So capital F x of f. This is what? 1 by 2t minus 1 by 2t, and this is 1. So what I told that it will give the area. What is area? So this is area is nothing but 1 by t into 1, right? And sync. And this is sync f. So this is in t. And this is pulse width. So 1 by 2 plus 1 by 2, 1 by t. So yeah, so it is 1 by t, sync t by t. Okay, and if you want to write in the pi domain, so there's nothing but sine pi t by t. Yeah. So if you want to write in this term, then this will be going to 1 by t here. This is a formula terminology. So it is critical in reconstructing the signal in the digital signal processing. It's often used alongside with the convolution theorem. Okay. And applications include MRI imaging and audio signal reconstruction. Fine. If I talk about the periodic signals, okay, so first of all, I will just go with um the Fourier series, then I will talk about this particular thing. Okay. So the key idea of the Fourier series is a way to represent what I told is a periodic function as an infinite sum of sines and cosine of the complex exponentials. So it arises naturally in solving boundary value problems in partial differential equations and signal processing. So remember these things. It's it's helpful in solving boundary value problems. It's helpful in solving differential equations. It's helpful in signal processing. It's many more fields. So Dirichlet's condition again it should be piecewise continuous but on one period. It should have max finite number of extremas and discontinuities, and the Fourier series converges to this particular point and this one things. So you should remember these things. Now, trigonometric Fourier series. So any function which is periodic in the time domain can be represented as fx is equals to a naught by 2, uh, a naught by 2, here a naught by 2 is there, okay, plus summation of n is equals to 1 to infinity, an cos nx plus bn sin nx. Okay, nx, an sin nx plus bn sin nx. Okay, an cos nx plus bn sin nx. So whereas the an is associated with the even terms, the bn is associated with the is associated with the odd terms. So an is 1 by pi minus uh, minus integration over minus pi to pi fx cos nx, whereas bn is this particular formula 1 upon pi integration over minus pi to pi fx sin nx, whereas a naught is 1 by pi minus pi by pi to fx dx. So AN consists of the area. Okay, first of all, you are considering one area of a signal. So that is representing the first term. Okay, this is area. Rest other you're taking care of AM by 2 or cos by 2. So you have to remember this particular thing. A not, so how will you remember? So first thing to remember is area. So even if you multiply 2 here, one remove 2 from here, then it is area. So integration over minus pi to pi, this is an integration over one period, fx dx. Okay, well and good. Whereas for the even term, you are doing 1 by pi minus pi to pi, fx cos nx dx. Okay, so for every signal, you need to write in this particular form. So if you see the coefficients in capture the cos component of function. The cos is actually the even function. So it captures the even components of that. Whereas the coefficients of Bn captures the sine component. Whereas can be adapted to other periods L to L by scaling x2 by x by L. Fine, that is, you can ignore it, but please remember this formula. That's very, very important. Now I will tell you the another way to write the Fourier series. So the same periodic function fx of period 2 pi. So here it was a period of 2 pi. That's why it is talking about minus pi to pi. Okay, it's period of 2 pi. That's why. Suppose it is period of pi only. So it should be 0 to pi. Okay, if it is period of something t. So should be integration over t. Now it should be 1 by 2 by t. So if I talk about simple t, so A naught could be 1 by 2 by t, integration over t, xt dt. An is 2 by t, integration over t, xt cos nxt, nxt dt. So cos nx dx, because we are talking about x, sorry, it's in the function of x, not t. But if it is t, to cos nt dt. Okay, so this t, a, an. Bn is nothing but 2 by t, integration of t, xt sine nt dt. So here my function is function of t. So this is xt. Whereas if we take x, so it will be the function of x. Cos and x will be the function of x. Okay, so this is a simple formula that you have to take here. Okay, well and good. So if you want to write in the forms of exponential, because as we know, the exponential can be represented in terms of sine and cosine and the vice versa using Euler's formula. So, uh, so fx is minus infinity to infinity, cn I e power I n x. Whereas here you are representing to this 1 to infinity. Here a naught by 2 for n is equal to 0. Whereas here it is 1 to infinity and 2 by t is common here everywhere, and a naught by 2 is there. Okay, but here is minus infinity to infinity, as cn is nothing but a fx e power minus I n x dx. Integration over one period. So it is integration over one period. This integration over one period. Fx e power minus I n x dx. So this is 2 pi is period, so it's just t pi. Okay. And relation to trigonometric form is Cn is equals to nothing but 1 by 2 An minus Ibn. Okay, whereas C of minus n is something but 1 by 2 An plus Ibn plus Ibn. So An minus Ibn 1 by 2 is nothing but Cn. This shows how to go back and forth between the complex form and the sine cosine form. So it simplifies the manipulation of series, especially in the differential equations. So you can represent in either form. This is exponential form. The other one is a sine cosine form or trigonometric form. It's represent. Okay. So Fourier series decompose periodic signal into sum of simpler periodic functions, it is sine and cosine or the exponentials. So it's decomposed the very used function into simpler functions. The convergence depends on the smoothness or the continuity. Dirichlet condition. Trigonometric and exponential forms are equivalent representation. They can be equivalent representation an minus ibn, or cn minus n is nothing but an plus ibn, you should know. So for example, like fx is equals to x, and it is extended periodically. So this just x. So you can write the trigonometric form like this. Okay. Why is cos term is 0 here? What do you think? Why it is 0 here? Cos. How fx equals to x looks like? This is x, right? For x equals to 1, this will be 1. Because for x is equals to 2. Because this is the odd function. Because fx equals to minus f of minus x. So it will only consist of sine function. Okay? So it's just sine. Whereas area under particular, this will be 0. So a naught will be again 0. The first term is 0. So again, it is only consists of the sine function. Cosine an will be again 0 because this is not an even function. Bn will only be there. So this is just associated with sine. While Bn has above pattern. Okay. So I'm going back to what if there is a signal that is periodic in the time domain, and it's periodic in a time domain, and you want to calculate its Fourier transform. How will you calculate? So the periodic function, which is in the periodic in the time domain, we will represent it in the terms of Fourier series, isn't it? The same way here that we did e power j 2 pi n f naught t. So that was n x was there, but you can also write, because here this is the dimple t was there, e power j 2 j omega f naught t. Okay, because f naught is a fundamental frequency. Fundamental frequency. So xt in the Fourier transform is nothing but minus to infinity. Cn e power j 2 pi k. I represent k or n f naught t. Okay, and the Cn is nothing but the an, sorry, 1 by 2 an minus jbn, or c of minus n is nothing but 1 by 2 an plus jbn, and an is nothing but Cn plus c of minus n, right? Whereas bn is nothing but c of n minus c of minus n, right? That is j. Okay, so that is one of the way to represent and cross connected the trigonometric parameter exponential form. So these are the Fourier series coefficients. So now if there is a, then in that case, the periodic signal will be represented in terms of this, and this every frequency component will be converted to Fourier transform, and that will be very, very easy because that is a sum of cosine and cosine. It's sum of impulse functions, impulse function, impulse function. So if it is a periodic signal, sorry, if it is a periodic signal and if it is representative of sum of sine plus sum of cosine, then it is just delta f plus f minus f naught plus delta f minus plus f naught plus delta f minus 2f naught plus delta f plus 2f naught, and so on and so forth. Okay, so if you see the time domain, so this is this, 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 this is this. Okay, because it's just a final, it's just an integer multiplication of the fundamental frequency. Okay, so that's very easy to handle those type of things. Okay, now Fourier transform examples, if you see, you know all this already. It's 1 plus j omega. It's why I created this particular slide, because it models a damping in the physical systems. Damping in the sense that if you have this particular this A determines the damping factor. Okay, complex signals. So e power minus at cos 2 pi f naught t. So this is giving the frequency translation. So that uh, that shifts the frequency from f to f naught. Okay, so f minus f naught. So it shifts the frequency from f to f minus f naught, as you can see from here. How is it shifting this way? Do you have a question how to solve this question? So I'm solving for you. So let us solve this question. So what is that? Xt is equals to e power minus at f naught t, isn't it? So how will you write this? Xt e power minus at. So this is nothing but e power j 2 pi f naught t plus e power minus j 2 pi f naught t divided by 2. Okay. And so 1 by 2, let us keep it out. E power minus at e power j 2 pi f naught t plus e power minus at e power minus j 2 pi f naught t. So by using the shifting formula, shifting, where xt is nothing but e power minus at and xf is nothing but 1 upon a plus j omega. Okay, or that is nothing but 1 upon a plus j 2 pi f. Okay, and since this is multiplied by this particular factor, so this is giving to, so 1 by 2, since, let us write this, the since whenever we multiply e power j 2 pi f naught t into xt, then xt goes x f minus f naught. Okay, and if it is multiplied minus j 2 pi f naught t, then it goes, this is Fourier transform, this is Fourier transform, this go x f plus f naught. So this particular equation 1 will goes to frequency transform to 1 by 2 out. This is x. This is that a plus j omega. So it is a plus j 2 pi f minus f naught plus 1 by 2. So 1 by 2 is out again. So a plus j omega j 2 pi f plus f naught. So the Fourier transform of e power minus at cos 2 pi f naught t is 1 by 2 1 plus a j omega or 2 pi f minus f naught plus 1 by 2 a plus j 2 pi f plus f naught. So what you're seeing is the cos term multiplication changes it properly, the frequencies of these two particular functions. And if in a similar way, if you multiply with respect to e power minus at sine 2 pi f naught t is equals to 1 by 2 1 a plus j omega f minus f naught. Here it is minus, it's not 2j, it is 2j 1 by a plus j2 pi f minus f naught, sorry, f plus f naught. Okay, so you can cross verify, but I'm sure it is this one. Okay, I hope you understand how to solve for a frequency domain transformation. Okay, So there's one very interesting thing to note is frequency time uncertainty relation. That uncertainty principle sets a lower bound on simultaneous localization in time and the frequency. So in mathematics, what it says that uh, del t multiplication with del f is greater than or equals to 1 by 2 4 pi. So example, short time impulses necessarily have the wide frequency spectrum. So what I mean to say is if it is del t, del f should be greater than or equals to 1 upon 4 pi. So it says that del t should be greater than or equals to 1 upon 4 pi del f. Very good. So yeah, what I mean to say is if you have the short time impulse functions, battery is getting discharged. So sorry for saying. Short time impulse functions have wide frequency spectra, or whereas um, and vice versa. So we'll see some of the examples here. So it is derived using the properties of Fourier transform of the Cauchy-Schwarz inequality. So what does the Cauchy-Schwarz inequality states are? Okay, yes, you can ignore this Cauchy-Schwarz inequality, but yeah. So the function xt with equality with the Gaussian function attains a minimum bound of this. So analyze a Gaussian pulse to illustrate the uncertainty equation. So del t is nothing but 1 upon 2 pi 2 root pi, whereas del f is nothing but 1 upon 2 root pi. So it is giving this particular formula. This is the optimal case why Gaussian pulses are used in time frequency analysis. Because del t, del f should be greater than or equals to 1 upon 4 pi, but in Gaussian pulses, you are having del t, del f is 1 upon 4 pi. It's very nice. So we already saw this. So there are some topics on filters. So I will take this later. Filters, how filters are used and what is the use of frequency and Fourier transform in the filters. So mm. So there are some questions that I will deal with. Okay. So compute the Fourier transform of xt equals to e power j omega naught t. So if we represent xt is equals to e power j omega naught t, that we can represent a 2 pi f naught t. So it's just multiplication with 1. So xf is nothing but what? Del f minus f naught. Isn't it? Okay. The Fourier transform is x del f minus f naught. And if you want to write in terms of free omega, so as we know, omega f is equals to 2 omega by 2 pi. Okay. So, and del at is nothing but 1 by mod of a del t by a. Okay. So utilizing it here. Okay. So if you want to write in terms of omega, so 2 pi. So it will be multiplied by 1 by 2 pi here. And then omega by 2 pi and omega naught by 2 pi. Okay, done. So same only, okay, 1 by 2 pi, and this is nothing but f only. So f minus omega naught by 2 pi. Answer is correct. So utilizing it here, simple formula, and we obtain in the distribution sense, and this is the answer. Very good. Solve this question. How will you solve? So using Euler formula, you need to write in terms of e power j to pi f naught t and plus e power minus j to pi f naught t by 2 for the cos, where the for the sine it is e power j 2 pi f naught t minus e power j 2 pi f naught t by 2j. Okay. And in that case, we need to uh, solve it for the first separately. Okay. So in that case, what will the formula? So answer is very, very simple. Del f minus f naught plus del f plus f naught 1 by 2. As for this, 1 by 2j del f minus f naught. Sorry, f plus f naught minus del f minus f naught. Okay. So waiting for some minutes for you to understand. Okay. And find the Fourier transform of a rectangular function. So this is nothing but a area into sink. This is f, and this is pulse width. So area for this one is 1. Area is nothing but t. Pulse width is also nothing but t. So x of f is nothing but t sink f t. Correct? Whereas sink x is sine pi x by pi x. So as we know, so what is the formula for sine x by x? This is the sampling function. This is sink function. So this is 1 by t and 2 by t. So where if if it is sampling function, then it is pi 1 by pi will be here, and this is pi pi. So okay. Determine the Fourier transform of sink function. Again, it will be same. This is, so how will you write this? Pulse width is what? Pulse width is 1 by t. Okay, and this area is 1. So uh, area is nothing but area is 1. So amplitude into pulse width is equals to 1. So amplitude is nothing but t. So rectangular will have the amplitude as a, and pulse is 1 by 8. So t from mod of t must let be less than equals to 1 by 2t, otherwise 0. Otherwise, so x of f, isn't it? This f, right? Same. Transform pair also or dualities. Okay. So if you have any doubt, you just tell me. I think Chaitanya only joined, but still, if you have any doubt, you can just tell me. This is a very interesting question. How to solve this? Question number 5. It's very interesting. Very, very interesting. Compute the Fourier transform of xt. So in order to solve this, we need to compute by using simple formula. So e power minus t, what stays that? E power minus mod t stays that e power t, if t greater than or equal to 0, and e power plus t if t less than or equal to 0. Like mod function, you know, no? T, so stay. Okay. So simply using the formula minus infinity to infinity, x of t power minus a 2 pi f naught ft dt. This is xf. So if it is minus infinity to infinity, e power minus 12. So I make the connectivity and yeah, 2 pi f t dt. Okay. So uh, so this is 80 e power minus 80 dt, isn't it? So 1 upon 1 plus j 2 pi f. Whereas this can be represented as minus, okay, so this will go here. This is a plus j omega, and this is plus 1 plus a minus j omega, j 2 pi f. So this is giving 2 by 1 plus omega square. So that's very interesting to note. So e power minus t Fourier transform is 2 plus 1 plus omega squared. This is 2 plus a plus omega square. Here a is nothing but 1. But you remember this formula, nothing but 1 plus a plus omega, isn't it? 0 to infinity. So even if you do minus infinity to 0, this is going to be coming the same. So this is a ut, so a plus omega, that's why it's there. Okay. This is also very interesting. What is the Fourier transform of ut? So this is ut t, and this is 0. So any function is determined from minus infinity to t. This is 1. Okay. So how will you write in terms of ut? Sorry. Hmm. How will you write in terms of UT? Hmm. Because we know UT is actually an integration of del T. So whenever we talk about integration, so if integration is written xt dt, so in Fourier transform it's just a multiplication of 1 upon j omega xf plus x of 0. Okay, so yes. So yeah, so it's 1 by 2 x of 0, I guess. Some formula is there, x of f. So xt is nothing but del t here. So x of f, here it is 1 by j omega del f plus 1 by 2 x f. Okay, yeah. So it is 1 by j omega plus del f by 2. You remember this in sense of distribution where it is interpreted in terms of Cauchy principle. So UT is having this particular, in fact, it's solved in class also. So 1 by 2 del f plus 1 by j omega. Okay. Why 1 by j omega? Because UT is 1 here for positive frequencies or the positive time. So it is just multiplication 1 by 2f plus plus x dash by 2. So that's why x dash is nothing but del f, and this is here. So I'm writing it again for the confusion, for removing the confusion. So since UT is nothing but integration of del t, okay. So del t has the Fourier transform of 1. So it is multiplied by when? J omega into x of f. So plus x dash of 0 by 2. So 1 by j omega, this is nothing but plus, and this is 1 only, del f, del t has Fourier transform of 1. Fourier transform of 1. So plus delta by 2, del f by 2. Will end. Now Fourier transform of ramp function. Again, we need to go with the formula. This is RT, T, this is T. So minus infinity T power minus J to pi f T dt. So it is 0 to infinity because it is ut. So T power minus J to pi f T dt. This direct integration leads to 1 upon 2 by f square. So direct integration. So yeah. So for this integration, what you need to do is uh, there's one formula for first function and second function. So first function, second function. U dv. So this is suppose this is v minus du by dv v dv. So using this formula, you will get this. Since the charge is very low, so I'm just giving it. If you don't know, understand it, you just let me know. Come back again in the next class. I will be there for you. Okay. So with the appropriate interpretation at f is equals to 0 in the distribution sense. Now, very interesting to know. So as we know, e power minus, sorry, a but I have it as 1 by. My internet connection is going again and again. So, yeah. So, if you say it will have e power, okay, find xt 1 by 2, because this 2 will go here. So, e 1 by 2 e power minus t, using the simple formula. Okay, 1%. Last question. So for an RLC circuit with an impulse input, determine the transfer function xf using the Fourier transform methods. So suppose you have RLC circuit, you will have xf of this. So RLC means R L C, and this is xf. So what I need to say is this is V, this is R, this is L, this is C. So voltage across this capacitor is VC is equals to C dV. Sorry. Voltage across capacitor is I dt 1 by C. And this voltage across conductor is L dC by dt. Using this formula, we need to compute this. The HF is nothing but this. Some questions are also more questions are there, but one question consists of 10 questions. So you can see I will keep it this one charging. Just give me some seconds. I'll come back to you. I'll share my screen for some of the practical examples. Uh, Meanwhile, you please see this particular code. This is simulation of Fourier transform topics in Python. So we will deal with it properly, uh, more understanding. So just give me a second. So for example, here we are having simulation of Fourier transform topics in Python. This script demonstrates Fourier transform of common function using FFT, inverse Fourier transform, examples including cosine, sine, rectangular pulses, sinc functions. So let us see this. So import numpy as NP, matplot, pylib, pylot, pyplot as PLT, scipy dot FFT import, FFT, IFFT, FFT shift, FFT frequency from scipy dot signal import windows. So compute the FFT of a signal xt and plot its magnitude and phase. There is array of signal samples. This is a time vector that is used for plotting the time domain if needed. And we have title strings also. So title string used in plots, that is n is equals to length of x, compute FFT and shift zero frequency compared to center. Then we have frequency is equals to FFT shift, FFT frequency and DT, PLT dot figure size, then PLT dot subplot 1, 2. So here we can see plot space and magnitude and phase spectra. So different frequencies are there. So for example, here cosine signal magnitude spectra is mod of XFF. Cosine signal frequency phase of X of F. Then sine signal. Observe this. How will you observe? What is phase spectra and what is cosine signal spectra? S- Simulating sine cosines, simple cos magnitude phase spectra. So this is sine magnitude spectra, signal phase of XF, then time domain signals. So time domain signal, cos and sine. So these are 90-degree phase shift. Rectangular pulse of XF. So rectangular person time domain, simulating sinc function. So space, sinc function, space of xf. This is showing what? 0 radian. Sinc function in time domain. It is like this. So 1 by t 0, 0, you see 0 cross. So it is 1 by t, 1 by t should be there. Simulating x of minus t. So the Fourier transform of that was 2, 2 divided by 1 plus omega square. Okay. So it is showing like this thing to note. So this is having time domains like this. So you can see it's e power minus parabolic or inverse parabolic. Whereas you see this e power minus at ut mod of xf, e power minus at ut phase of af, e power minus at ut in time domain. This is e power minus at ut in the time domain. Unit step function, mod of xf, magnitude and phase spectra is different. So magnitude spectra is always even, whereas phase spectra is odd in nature. Here's a unit step function. This is unit step function, how it looks like. Then ramp function. Uh, Again, the phase and magnitude spectra. So after calculating the frequency domain transformation or after Fourier transform, you'll have omega term. So whenever we do mod like 1 upon j a plus j omega, then the mod of a plus j omega is 1 upon root over a square plus omega square. Ramp function in time domain. Simulating inverse Fourier transform example. Uh, Inverse Fourier transform comparison. So simulated inverse Fourier transform. That analytic 1 upon 2 pi e power minus mod t. So this is simulated one and this is analytic one. So it's different. Maybe varies with respect to the actual thing. So RLC magnitude circuit, and this is the phase circuit. So phase rises from 0 to zero point 0.4. Magnitude decreases continuously. Magnitude comparison, phase comparison. FFT of derivative. This is phase comparison. Delayed signal 1 seconds phase of accept. Delayed signal. This is delayed signal time domain. Simulating cos square 2 pi f naught t. These how signals looks like in time domain and the frequency domain. This is whenever we talk about magnitude and phase vector, that is in this frequency domain. Cos square 2 pi f naught t in the time domain. This is just see this ones. Cos square 2 pi f naught t in time domain. So this is a modulated version. Modulated signal in time domain. Normal signal in frequency, their magnitude spectra and this moderate signal. So as we know, whenever the signal is multiplied by cos 2 pi f naught t, so it is the frequency spectra is shifted from plus f naught to minus f naught to frequency spectra is shifted. So it is moderated signal in time domain. Original signal phase of xf scaled to t to x to t phase of xf time scaling. So inverse recovered signals are same analytical in this impulse train. Very good thing to note this is so Gaussian signal, as we know, the Fourier transform of Gaussian is Gaussian for magnitude spectra this, and Fourier transform approximation of source square is. So this is very interesting to note. Fourier series approximation. Okay. So when we sum the sine and cosine infinite number of times, so that is terms to square exact wave. So Fourier series, any number of terms is 1, number of terms is 5, the number of terms is 51. So red color. So it is almost approximating. And if we change it to 100 or 200, it is approximate, it will approximate. For the Gaussian signal, we have x t is equals to exponential e power minus pi t square. This Fourier transfer is proportional to this one. In our simulation, the FFT approximates the continuous transform of two scaling factors. So Dirichlet's condition explanation, a function Fourier transform converges if it satisfies these conditions. It has finite number of discontinuities. It has finite number of extremas. The function is absolutely integratable. The square wave meets all these criteria. And the plot, you see the Fourier series, some partial sums converges to square. So there are some low pass filter, high pass filters, and all those things. We just see and how frequency, magnitude, and phase spectra is utilizing that. Then we will end the class. So I have covered almost everything, whatever was there in the week 3. So Fourier transform and its properties, then Fourier series and its properties, then some of the examples I solved, then with real-time applications I solved. Then we discussed about the 10 questions that will be helpful for you to solve the week 3 assignment questions. And finally, we discuss the Python plots for all the functions. So I think thank you so much for joining. And if you join, it will be super helpful for me. And yes, thank you so much. So I will end the class now.